Hi, everyone, and thank you, Jonathan, for the introduction. This is Min from Databricks, and today I'm going to talk about the TiDB at Databricks. First thing first, let me, okay, so it doesn't work. Let me make an introduction of our company, Databricks. So Databricks is a big data and AI company, and we are created by the original creator of Spark. And right now we have so many open source projects like Delta Lake, ML Flow, blah, blah, those. And we're a global company with about 5,000 customers and also 450 plus partners. And our company runs Spark cluster in cloud and also Databricks SQL is a data warehouse solution and also AI solution. And yep. And next is the MySQL at Databricks. Right now, we use MySQL in many places. Majority of the MySQL data are the control plane data, service data. So we store our account data, Spark cluster data, Spark job data, as well as SQL history and SQL catalog data, and also the other data in MySQL. In terms of the scale, we have around 100 regions over 3 clouds across all over the world, including the AWS, Azure, and GCP. So in each of the region, we have multiple MySQL instances on that because of the scalability issue I will mention later for MySQL. Roughly, we have about 100 terabyte data on MySQL totally. That's the data at MySQL at Databricks. We have been seeing many problems with MySQL. The majority of the problem is the scalability in terms of the storage and CPU memory and also the connections. So we can see like there's so many servers and they connect to MySQL and they're limited by the connection. And so we want to find alternatives that is horizontally scalable and highly available, and then strongly consistent, and also is fully compatible with MySQL. So after search around and a lot of research, we figure out TiDB is our answer. And today, my session will cover 3 parts. We'll break down into 3 parts. The first part is infrastructure, discussing how do we deploy TiDB in our Kubernetes cluster, and then also how we maintain it. And the next part is the performance and how we tune TiDB on Kubernetes. And the last part is migration, how we migrate from MySQL to TiDB. Okay, that'll work. Okay. This is the challenge when we maintain TiDB. The first thing is when we use MySQL, we use cloud manager, manage the MySQL, for example, AWS RDS or Azure MySQL. But right now, we will maintain our TiDB ourselves. So we need to maintain the HADR ourselves. So it also will bring significant operational overhead to us. And also, because TiDB is more scalable and then MySQL, we are considering consolidate all of the MySQL instance into one TiDB cluster on each region. So, but the sharing will also give us the penalty of isolate of the for example, there's a bad query, they can occupy all of the resource. So we need to think about the isolation as well. And also, because our services are deployed in Kubernetes, so we want to deploy the TiDB in our Kubernetes cluster as well. So those are the challenges we are facing when we deploy TiDB at Databricks. And And this is our architecture. Because of some historical reason, we launched a dedicated Kubernetes cluster on the right side for TiDB only. And then our service, contributing service, will be on the left side. For example, the cluster manager, the jobs manager, and also the Spark SQL, Databricks SQL will be also maintained in control plane Kubernetes on the left side. It will send the SQL request to the right side. So between these two, we have a load balancer, and the load balancer has a service IP and service endpoint. So the SQL will flow into the right side of Kubernetes. And inside the Kubernetes cluster, we have one TiDB operator in each of the region. And this operator maintains multiple TiDB clusters. Each of the TiDB cluster will in one Kubernetes namespace. And inside the namespace, we have several TiDB components, which mentioned by Jonathan. So that's PD, TiDB, and TiKV. And also we maintain the TiCDC service for replication. I will mention it later for TiCDC. Okay, that'll work. Next. And because we need to build a highly available TiDB, so we think about whether we can torrent the zonal disaster. So we built this zonal redundancy. And we will deploy each TiDB component in each of the zone. And then if one of the zone fail, and the other two can take care of it. In addition to the zonal redundancy, we also build a regional redundancy. So basically we have two choices. The first one is we can build on top of TiDB because TiDB support Raft consensus. We can make this strongly consistent. But downside for this is because we have several regions. Between this region, we can see like a very high latency, especially in Azure. They can take up to like 500 milliseconds per network package. And also, another choice is we can use the traditional way, use binary log. We probably see some like lags or inconsistency, but we can torrent that. And also the major reason we chose the binary log based one because we have some internal tool running against the MySQL. Which can replicate MySQL data from one region to another region, and they can pair together. So we have active replication between the MySQL. So we want this TiDB architecture also work with our existing system. So we choose the binary log based replication for regional redundancy. Yeah. In addition to the HA improvement, we also ensure the durability. So we will do daily backup using the TiDB tool called BR, and we will do it daily and typically 7 days. Okay. Regarding to the failover, there are many kind of failures. For example, the container failure, the pod failure in Kubernetes, and also we will rely on Kubernetes to bring it back. And also Kubernetes node failure because TiDB operator using stateful set for TiDB, and they cannot recover the stateful set after Kubernetes node failure. We have some internal tool to look into the liveness of the node and then do the recovery for the stateful set. And the remote disk failure, which is real and is handled by TiDB. And then if there is a network partition, and the TiDB will become unavailable, but it needs some human intervention. And also we will do operations, and the basic operation include like TiDB upgrade. We will rely on the TiDB operator, which will do the loading update. And also the Kubernetes node update. For example, we want to upgrade the Linux kernel, or we want to replace retire a node. And then we usually do a loading update. And the process is we will bring up a new node, and then we will tend the one of the existing node, and migrate all of the pod into the new node. And after the new node is ready and TiDB component on that node is ready, and then we start another, and then we terminate the old one. We start a new process. And then this is the loading update for Kubernetes node. Okay. And then, as I mentioned, we need SOS isolation. We have two choices. The first one is we build up a two-tier TiDB clusters, tier 0 and tier 1. And tier 0 is support the critical services. For example, the cluster manager, the jobs, and those stuff. And then tier 1 is a shared TiDB cluster, is larger, and the less critical one service will share the TiDB cluster. And in tier 0, each of the service will be equipped with one TiDB cluster exclusively. For example, the cluster manager have one dedicated TiDB cluster for it in tier 0, and the jobs has one tier 0 TiDB cluster in it. This will build a fully isolation, but the downside for this is, for example, if you have a query that cross the isolation, or there is a service which is currently in tier 1, they share with the others, but as the business grows, it might be promoted to tier 0 service, and then you need to because data is not sharing between the clusters, you need to do a full migration from the tier 1 to tier 0. And so the second solution is a placement tool, a placement rule built in TiDB. The basic idea of placement rule is inside the PD, the brain of the TiDB, you can control the data chunk and map into a data node, the mapping between them, and then you can pin a set of data, for example, a database data, to some sort of a group of the nodes, and then this data occupy the nodes exclusively, but physically they are isolated with the data set, but logically they are still in the same TiDB cluster. So data sharing or query across data set, you can still work. But right now, the placement rule is still in development. And right now, we cannot use SQL to define the rule, or some limited SQL to define the rule. So it's still in development. It's not that mature. We're working with PingCAP to see whether we can test it in Q1 next year. Yeah, we're looking forward to it. Okay, next part is the performance tuning. Okay, so this is our initial setup in Azure. We have a bunch of TiDB nodes, a TiDB pod, and a bunch of PD pod and TiKV. Each of the TiKV pod is backed by 2 terabyte storage, and also we will use System Bench to benchmark it. The workload is picked up from our internal SQL history service, and we use System Bench to simulate the traffic, but with very high concurrency and with very high traffic, like 10x time than our regular traffic. The first thing we figured out is we want to figure out is whether we want to use local NVMe disk or remote disk. After our benchmark, we can see the local NVMe has better performance, but it will give up a lot of operational overhead because it's local. If we want to terminate one instance or one node, we need to first copy of the data, the entire node data, and migrate from one node to another node. But to terminate a node is usually not under our control in cloud because the cloud provider might retire some of the data, ton of the nodes, and then usually they are not terminate one of the nodes. They will terminate many of them, right? And then you will lose the 2 copies of them. You will lose the consensus. So, there's no choice for the local NVMe in cloud. So we decided to use remote disk. But remote disk has, although it has less operational overhead, we can like detach the disk before the retirement, and then we can reattach to another new node. But it has poor performance, especially in Azure. Okay, and at the beginning we get this number 4K TPS 682 millisecond, but make a declaration. We are run it on Azure. AWS EBS is much better, and also we are running very high workloads. So regular workloads are much better. And also this is write intensive. The reading, because most of the reading is read from memory. So the read is very good. It's like much better than MySQL. And then if you are on regular workload, the write performance is slightly slower than MySQL, but this is very high traffic. And we can see this number. 682 milliseconds, that's very long time. And then we look into the Azure portal, the website. So we can see the remote disk typically take about 1 millisecond per disk write. But why is it reflect into the end-to-end query latency to 682 milliseconds? So we will try to answer this, and we try to figure out what happened inside. And then we look into the TiDB write path. So you can see, I will take a brief introduction for this write path, and Yi will introduce more about, dive deeper into this. So when the query comes into TiDB, it will served by the TiDB server on the left side. This is a stateless query engine for TiDB. And the query will be parsed by a SQL layer and then come to the phase committer layer. And then we'll send to TiKV. And inside of TiKV, you can see from the right side, there are a bunch of worker group, schedule worker and a storage worker. And between the worker, there are some queues. And then the storage worker will write data into 2 places. The first place is the ref log. The ref log and the real data will be right into the KV storage. And both of them are backed by RocksDB. So on the left side, the ref log is right in RocksDB, and also the KV side is also right into RocksDB. Okay, and the first thing we can think about is because we are writing to the same storage, and the RefDB and the KVDB are sharing the same disk. Whether we can separate them to get a better performance, yes. And then we do a separation. We create a dedicated remote disk for the RefDB. That's because the ref log is very small. We just need 64 gigabytes storage. and then still keep the 2 terabyte for the KB storage. Then we can see, and also we did some other configuration optimization, for example, the bound, the slope, and TiDB tuning. And after that, we can see 7.8 TPS and 451 millisecond for our workloads. So that's nearly double the TPS, the throughput, and around 30%, 33% improvement on the latency. But still, it's not enough. And then because 450 milliseconds is still a very long time. Then we look into the metrics provided by TiDB. So one thing we noticed that is the scheduler queue. As I mentioned, in the TiKV layer, there are a bunch of worker groups, and between the worker group, there are some queues. So we can see these 3 TiKV pods, each of them have in average 1,000 operations executing. And then we look into the I/O, the other stuff. We can see the I/O is low, but how it reflects to the end-to-end latency, 451 millisecond. And then we come up with a hypothesis. The hypothesis is because of the lower layer disk I/O, it's very slow, and then all the requests is like queuing up in this queue, and then you can see from the end-to-end query latency become very slow because of their queuing. And in order to confirm that, we take a look at the low layer, and then we did some profiling. And then one thing we did is we use I/O top. And then from the I/O top, we observed that there's at a time there's only one single thread is working on this I/O. And then we did a perf profiling, and we can get this result. We figured out almost all of the latency is coming from the disk layer. These 2 parts, you can see on the right side, that's because of the ref log. They need to flush the data, the ref log, into disk. So there's a wall F data sync. And because of this wall, it also triggered the left side, the file system journal log for the wall. So both of them are single threaded, and they are serialized. So each of all the other requests queued up. So we want to find a solution for it. The first workaround we can think about is whether we can do it very quick in the short time and from the hardware. So whether we can parallelize these wall logs. So the first idea is we can use a smaller instance and smaller storage. For example, in this case, we launched 6 TiKV pod, but each TiKV pod is with half memory, half CPU, and half the storage. For example, we allocate 1 terabyte for each of the TiKV pod. Then we can get a very good performance. That's around 13K TPS and 314 milliseconds. That's another roughly double of the TPS and another like 30% improvement on the latency. Yeah, I think because hardware is easier, but I think we have another idea that from the software. Because right now, in each of the nodes, we have only 1 RocksDB, 2 RocksDB instance, 1 RocksDB instance for all of the data ref log. Whether we can create multiple of them, for example, 4 of them or 16 of them to parallelize the ref logs. Because and then we can parallelize the disk write, right? But this, if we do this, it will modify the TiDB code, and then also it will cause some like compatibility issue with the old TiDB version, because it will change the data format in the disk layer. This is our prediction. So we predict that we can get this this latency. Okay. The last part is migration. The migration is we use the replica based. With the migration, we have two stages. The first stage is pre-checks. So we will make sure TiDB will work exactly the same as MySQL. So we will change our unit test, the MySQL unit test, and then be backed by TiDB. We run all of the MySQL tests against the TiDB to see whether it has a compatibility issue or not. We've been seeing some, but we have some workaround. And also we will launch we have some internal tool that can launch all of our control plane service in one Kubernetes cluster and for testing, and that backed by MySQL. And then we can change it into TiDB and then run the same integration test against TiDB to see if it behaves the same as MySQL or not. In addition to that, we add an interceptor layer, a wrapper, to our data access layer. That's the data source on the right side. You can see from the diagram. We add an interceptor. This interceptor will replay the traffic, the SQL traffic, and then write to in Kafka. And then we will create a dev MySQL and also will dev TiDB for testing. For testing purpose, we can compare the two. And we will launch a consumer which will replay the TiDB traffic and then write into and read from MySQL and TiDB. And also we use the TiDB tool to compare the data between the test MySQL and test TiDB. So after done those pre-checks, we will move to the actual migration. The migration is replica based, as I mentioned. We will use TiDB built-in tool. It's called DM, and that's for data migration, which can help you to do an initial dump and the incremental replication from MySQL to TiDB. And then after TiDB is a catch up, and then we did some like necessary checks. We will do the cutover. We will cut over the MySQL client from pointing to the MySQL to TiDB. And then at that time, we will also do a in-reverse replication, because from TiDB to MySQL, we will use TiCDC here to do the in-reverse replication. That's for the case of rollback. If everything, like if after migration, everything something is messed up, so we will still have a replication from TiDB to MySQL, and then we can fall back to MySQL after migrations. Okay, that's all of my talk. Okay, any questions, feedback?
Thank you, Min. That's been great so far. Yeah, really appreciate that. We do have a couple questions from the audience. Let me just get to them right here. Lost my Zoom. There we are. Okay. So let me ask you the first question that came from the audience. Manish asked, are the 2 terabyte and 1 terabyte storage shown, are they single cloud disks?
Yes, they are single cloud disks. So we will use the persistent volume. This will launch 1 terabyte each, and then each of the 1 terabyte remote disk will be attached to the instance. Okay, and also the instance only run 1 pod exclusively for the performance.
Okay. And he also asked, what kind of a file system are you using?
Is it again? Cloud system?
What kind of a file? Are you using any type of file system underneath
Oh,
this, or is it all raw?
EXT4. Right now, we use EXT4.
EXP, okay.
Yeah.
Great. Rui asked, is RocksDB a performance bottleneck in practice?
In practice, in regular workload, RefDB is not. But if you have very high traffic, especially on writing traffic, for example, you have like 800 concurrent writing to the TiDB, you will see the Reft is the bottleneck.
I see. So did you get just to follow up that question, did you find that RocksDB was that there were write performance issues when you had them both shared? Is that why you separated them?
We still see very high like this IO from the ref log compared to the KV, because the KV you can store it in memory first and then flash if the memory is full, like every 32, I don't know the number, let's say every 32 megabytes, I take a flash. But ref log, you need to sync it every time because it will keep the consensus for you. So that part of IOPS from the ref log is very high. Although the storage is very small for the ref log, but the IOPS is very high.
Yeah. Okay. So Andrew Wang asked, did you run into any issues setting up your MySQL to TiDB or TiDB to MySQL application?
Yeah, because we're using Flyway. And Flyway have a lot of schema migrations. And for example, we used to do some like incompatible schema migration. For example, I delete the primary key and then I add another primary key. That is not supported well by TiDB. And also, if your query has some stored function or triggers, that's not supported by TiDB. And another thing I want to mention is a foreign key constraint. It's not supported well by TiDB right now. But right now we don't need it because we don't have those foreign key constraints.
Okay. I have time. I apologize. We can't get to all the questions we have out there. I have time for one more question. Huxon asked one rather technical question, but I like it. Does the write transaction wait until all the bin logs applied on the remote replica, or just until bin log materialized on the remote replica?
That part I think I can ask the TiDB.
Okay.
That's the Reft, how the Reft works. So
yeah, sounds like something we'll ask.
I can answer, but I don't think I don't know whether I can answer.
That's okay. Or not. Well, that's good. That's a really good point. We'll have the TiDB. I'll ask the TiDB engineers to get back to posting those questions later.
Yeah.
Okay. So, ladies and gentlemen, thank you so much and Min, thank you very much for your presentation. That was excellent for Databricks.
Thank you, Jonathan.
Thank you very much.